Welcome to our video here on optimization from Cranky Calculus. We're going to go ahead and get right into this thing. Don't forget to like and subscribe for more videos like this. Optimization, you can see it's kind of wordy right here. It is a lot of important stuff in terms of you need to know geometric shapes and you need to know formulas like distance formulas and stuff like that. Big thing here with optimization, I know there's a lot of writing right there on the screen for you, but you can read through that on your own. You have to know the difference between an optimization problem and a related rates. Optimization means we're looking for the best of something. That best can be the highest, the lowest, the smallest, the greatest, lots of different ways to have the best, and you can kind of see everything in there. I also have the steps right there. I'm going to skip over the steps and get right to these problems just because I'll be doing the steps as I go through. So use this as a great reference as you're doing problems on your own, but I'm going to just skip on down to the problems right here, and let's get rocking and rolling. Okay, so these are non-calculator examples. I will do another video where I will show you how to do everything on the calculator. So for the first example we have here, we have the point on the parabola, or find the point on the parabola y equals 1/4 x squared that is closest to the point of 2, 5. So one thing that I talk about in the above slide is to draw a picture, because that'll help out a lot with what we're doing. So here's our function right here, 1/4 x squared. And then the point 2, 5 is going to be somewhere up here. What we're trying to do is find the distance, or find the point that is closest to this. So if I were to draw a little dotted line right there, we need to find whatever this point is on that graph. So in order to find that, we need to minimize our distance. So how do we know to do that? Well, we need to use the distance formula. So the distance formula that I use in calculus is slightly different than the distance formula you probably used in geometry. So the distance is square root of x minus x1 squared plus y minus y1 squared. So I'm already defining x as a variable and y as a variable. And what I'm going to do here is I'm going to substitute in my x1, y1 into this. And I'm going to substitute out my y variable, so I can rewrite this as d equals x minus 2 squared plus 1/4 x squared minus 5, and that is all being squared. Okay, so we got this nasty looking thing. The big thing for optimization is we want this to be a function in terms of either x or y or h or b, h being height, being base if it's something geometric, or t for time, whatever. So I do have this written out as a function in terms of x. So I'm going to call that d of x. It's not times x, it's d of x function notation, and I am going to do some algebra here because I don't think taking the derivative right now is going to be helpful because it's going to look ugly. So what we're going to do here is I'm going to expand the first term. So it's going to give me an x squared minus 4x plus 4. That's me expanding the x minus 2 squared all the way out. Plus, I'm going to expand this one. This is going to give me 1/16 x to the 4th minus, I believe, 10/4 x squared. I'm just doing that in my head real quick. Yeah, that's correct. And I will make that 10/4 look nicer and to be 5/2, and then plus 25. So that's me expanding both of those things. Before I take the derivative, I do want to combine everything. So I'm going to go with the 1/16 x to the 4th up in the front. I think that's good right there. Let's do my x squareds now. So I'm going to have, let's see, I have 4/4. So I'm going to get, this is, sorry, I'm just doing algebra in my head real quick. I probably should do this ahead of time. Negative 3/2 x squared. Is that right? You're not going to tell me. Minus 4x plus 29. Okay, so that's now our distance formula, particularly for the point in terms of where the location is on the graph. So what I want to do now is I do want to take that derivative, and I do want to see when it equals 0, and then I can go ahead and do my mini candidates test here to figure out where our point closest is. Okay, I just made sure I verified all my algebra is good here. I'm ready to take the derivative. We're going to set this equal to 0 to find our critical points. So the derivative here is going to be some chain rule. I'm actually going to have a denominator here, and the numerators, since we already have a square root function, the numerator is going to be the derivative of the inside. This is going to give me 1/4 x cubed minus 3x minus 4. And the denominator is going to be 2 all over this 1/16 x to the 4th minus 3/2 x squared minus, this looks ugly, but don't worry, we don't have to worry about it. So I know this because I've told you in my previous videos before to memorize the derivative of square root of x. Derivative of square root of x is 1 over 2 root x. I just use the chain rule, and I think it's much easier. You have that memorized because it's pretty easy to derive that. We're going to set this equal to 0 now. So when we do that, I don't care about the denominator equaling 0 because it's not going to happen. Distance is only positive. So we can only have positive distance, so a numerator is always positive. I'm not going to worry about it. So I'm going to care about the numerator. The denominator will always be positive. And this one kind of gets a little funky. And if you took AP pre-calculus, they don't teach you this little step here I'm going to go through. So I'm going to just real quickly solve this for you. So this is a tough one to factor. If you don't mind, I'm going to make that have a 1 in the front there as my coefficient. So I'm going to multiply everything by 4. So I'm going to get x cubed minus 12x minus 16 equals 0. And there is no way to factor this without using something called the rational root theorem and synthetic division. I'll kind of shortcut that one a little bit. But whenever your a term, which is going to be the leading coefficient, is 1, then you're going to look at the constant right here. And those factors, which are going to be possible factors, are 1, 2, 4, 8, 16. Those are the only potential factors that we have, positive or negative, which means that one of those is going to work out in a factor here. And then I can use long division to take out whatever that is. So as I'm looking at this, any one of those numbers go into that. And again, plus or minus. I probably should have put a plus or minus there so it looks a little bit better. So plus or minus. Okay, so plus or minus any of those. This is coming from the 16. And -2, I think. Am I right even saying that? I'm looking at the answers over here. Yeah, -2. So we found out that 2 is going to work just by plugging in, or sorry, -2 is going to work just by plugging it in. So that means that this is going to have a factor of x plus 2. So since this has a factor of x plus 2, let's do some good old long division here. Hopefully you remember how to do that from your AP pre-calculus. I'll go through it pretty quickly here. X squared is going to multiply through x plus 2, which is going to give me x cubed plus 2x squared. We're going to subtract that. There is no 2x squared term, so that's actually going to drop down to -2x squared. Drop everything else down with that. And then we're going to get minus 2x. So we're going to get -2x squared minus minus 4x. And we're going to subtract that all the way through. And we're going to end up with -8x minus 16, and then it looks like we're going to get -8 right here. It's going to end up with -8x minus 16. So we do know that x plus 2 is a factor, and it rewrites as this right here. Okay? So now in the red, I can actually factor that. So this becomes x plus 2, and then it becomes x squared minus 2x minus 8. And that does factor again. We set that equal to 0. That's going to give me x plus 2, I believe x plus 2, x minus 4. Okay? And that's going to give me x equals -2, x equals 4. And we can just do a basic little sign chart here. -2 and 4. Our end behavior, just from our derivative function up there, the bottom, again, is always positive. I don't think we're about the top. It's an odd function, so it's actually going to have a positive end behavior. And I was able to factor this out down here. And the x plus 2 is repeating, so we're actually going to change signs, and then we're going to stay negative the entire time right here. So we only have our only local min. If we just have one local extremity, it is the absolute minimum. So the value we want is x equals 4. Okay? So what's the coordinate point then? If x is equal to 4, then y is actually also equal to 4. So we're going to get y equals 1/4 times 4 squared, which is 4. So the point 4, 4 is the closest point to 2, 5. All right, man, that was a very pre-calculusly heavy problem there towards the end, but that's the basic idea for optimization for that problem. Next up, we got a problem here with a cardboard box with a square base and open top being constructed from 27 meters squared cardboard. Find the dimensions so that the volume of the box is as large as possible. Okay, so I'll do this problem in green here. So we are trying to find the maximum volume, it looks like. So find the dimensions that makes it as large as possible. So our volume for any box is going to be height times width times length. Or length times width times height, whatever you've been taught, okay? So we got to just figure out what everything is here. We do know that we do have a square base, so that means that our height is different from our length and our width. So we're actually going to say that our length is equal to, sorry, our width is equal to our length. Just for easiness here, I'm going to call that x. So our volume of this box is going to be height times x squared. I'm just taking that box and just extending it up, like squaring, extending it up. So that's pretty easy to figure out from there. We do need to know what our surface area is because we are given that part right here. So our surface area, SA, is going to be, if it's a cardboard box with a, and I'll draw this out, with a base of x and then a height of whatever variable, height of h. It's an open box. I'm going to have 5 faces on this box. You can kind of see them. One face right here, which is x times h, x times h on the face next to it, and there's 2 other sides on the other sides that are both x plus h, which means we have 4 x times h's plus our bottom part right there on the bottom, which is going to be x squared. So that's our surface area of this box. Kind of see it. So we do know that we have 27 equals 4xh plus x squared. Now I think it's easiest to solve for h and to eliminate h. So we're going to get 27 minus x squared equals 4xh, because the whole point of this is I want to be able to take the derivative not of multiple variables, of just one variable. So h here is going to equal 27 minus x squared all over 4x. So I can rewrite this volume as a volume of x, which is equal to 27 minus x squared all over 4x, and this is times x squared. Now, same thing that we had in our previous problem. Right over here, we were given our d of x, or we can find our d of x, but let's go ahead and rewrite it so that it looks nicer before we take the derivative. This one's not too bad. I'm actually going to have these x's cancel out from the denominator. It's going to leave me with 27 minus x squared times x all over 4, and this distributes to be, let's do 1/4 times 27x minus x cubed. And what I want to do right now is I want to take that derivative, and we're going to set it equal to 0. So the derivative of the first term is going to be, well, it's going to be 1/4 times 27 minus 3x squared, and we're going to set that equal to 0. So we do want to solve for this. I'll multiply both sides by 4, get rid of that 1/4. I do have 27 minus 3x squared equal to 0. I'm going to move that negative 3x squared to the other side, divide both sides by 3, and we're going to get x to equal plus and minus 3, but since we are dealing with volume and we're dealing with geometry, we're just going to have just a positive 3. If you want to do a bit of a sign chart just to check this out for our derivative, again, we're looking for the largest possible. We do have a negative x squared, so we actually have a negative end behavior there. We're going to change signs at 3, so this is going to produce a maximum. Don't need to verify it, but it's kind of nice to know why. And let's answer my questions. Find the dimensions. So if x is 3, that means that the height is going to equal, I have it right above me, so it's going to be 27 minus 3 squared all over 4 times 3, which is going to give me 18 over 12. So it's going to give me 3 halves. So x is 3 and h is 3 halves, and that's going to maximize our volume of our box. So thanks for watching here. Don't forget to like and subscribe for more content on anything and everything calculus.